Okay, cool. So let's try out some examples. So the classic one, and I think it's actually a really good one, especially as we're thinking about, like maybe like COVID testing, stuff like this too. But like, this could actually be true for medical testing. So pretend we test positive for some rare disease, right? So like, first of all, your feelings for like testing positive for a rare disease, probably not feeling that great, right? Like you're like, like this is not what I wanted to hear, right? And so the scenario kind of goes like, well, you get a call from your doctor, you get positive tests on this rare disease, and they say like, hey, this is, you tested positive. Your instincts is like, okay, like I have this disease, right? But maybe there's a chance the test messed up, right? Like no test is 100% accurate. So maybe there's a chance, like you're one of the rare examples, that maybe this happened to. And plus it's a rare disease. So, how likely is it you having this actual disease, right? So it's nice to kind of give a little extra numbers to quantify what we're thinking about. So we'll say the disease is rare. Rare is relative, right? But we'll say only 0.01% of the population has it. So of every, what's that, 100,000, every 1 out of 10,000 people have this disease, whether that's rare or not, we're just gonna go with it, okay? And then the test is 99% accurate. So it's important to actually note that when we say 99% accurate, this is important because we can have false positives and false negatives, right? So we're gonna say 99% just to kind of make it easy for us so we don't have to deal with it, is correctly identifies 90% of the time of whether you're sick or not. So meaning that if you are sick, 99% of the time it will identify, oh, you are sick, right? And then the other 1% time it'll say you're not sick. If you are not sick, right, and you're healthy, 99% of the time it'll say you are healthy, and 1% of the time it'll accidentally call you sick. Does that make sense? Cool. And know that those don't have to be equal, right? But I'm just making it equal because then it's easy for us to like do the numbers and stuff like that. Okay, so we can actually take all this information and we can actually take Bayes' theorem and actually update into having from our prior and our likelihood and actually find what the posterior. And the posterior, has anyone got an idea of like what the posterior would represent in this scenario? Like once we get a number, like let's say we get like 0.8, like what would that 0.8 represent? Yeah, it's okay. Good, however.
I was trying to work it out and I hit the button.
Oh, it's okay. It's an accident. It's like being called on when you like scratch your head and the teacher calls on you, right? No, that's okay. You can think of the posterior is what the likelihood of us actually having the disease. So that's kind of like, and so we break this down. I think I actually have it written down here. So let's see here. Oh, no, I don't have it right now. So you can think of it as our prior, or our posterior. Let's start with that because that's easier. What's the probability of us having or being sick such that we tested positive for the disease, right? That's our scenario. It's like we want to know, hey, am I sick given that I tested positive for the disease? How likely am I actually sick based on that I tested positive? Does that make sense? So that's our posterior. Yeah.
Mm-hmm. Like how do you know like whether B comes first or A comes first when you're like applying, like I understand that you have two probabilities A and B, but how do you know which one goes where? Like one in like yeah, how do you know which one goes where for like A and B?
Like you're talking about like this versus this?
The top equation. The left. Yeah.
How do you know? I wrote this twice. Sorry.
Oh, okay.
So obviously, this should be. Yeah, I don't know why I wrote it twice, to be quite honest. Oh, I just wrote it so I can have that division out here.
Yeah,
is that what you're talking about?
Yeah, but the point is the left side of the equation. How do you know which probability is A, which probability is B from the fact pattern?
Right. So it's more like don't think of probability, think of like the event, right? Is we can read this as the event A such that B is true. So the way you can read this is being like, what's the scenario? We tested positive for a disease, a rare disease. So what we want to know is what's the probability of us having this disease such that we tested positive. So in this case, we want to know A, the probability of A, which is the likelihood or the probability of us having this rare disease, and B being that like we tested positive for this disease. Does that make sense?
Yes.
And so
I got
that's, okay, yeah. And I think that's where this kind of falls together. It's that you always have two different events. You have the event you don't know, which is in this case A, right? We don't know A. We don't know, essentially what is the probability of having this disease. And then given that B happened. Does that make sense?
Yeah. So in this case, B would be 99%.
It wouldn't be B. B is the event itself. So another way to write this would be similar to, I'm trying to write it down, but I'm just going to type it because that's probably going to be quicker. So like you can think of it like instead of like probability of B like this. So like let's say we have probability of B. We can say this is equal to the probability, what did I say, B, test positive. Okay, so this is just probability of B is the fact that I test positive, right? Probability of A such that B is saying the probability of having the disease such that, or given that, sometimes you hear given that I test positive. Okay, does that make sense?
Yeah.
And so like this is where you should probably start off. Say, hey, I want to know the probability that I have the disease given that I tested positive. And then from there you can break down what is A and what is B. Well, in this case, A is that is I have the disease. B is I test positive. Those are the two events, right? Which you notice those don't have probabilities by themselves. But I could write down probability of B, I test positive, right? Which I actually don't know yet because there's different ways you can test positive. We'll talk about that in a second. But the probability of A, right, of having the disease, well, we know it's super rare, right? So it's like, what do we say, 0.01, right? So, or that's percent, so like that. So that would be probability of A, right? But probability B is actually a little more tricky. Probability B is that we test positive, but there's two cases we can test positive.
The total law of probability, law of total probability, right?
Right, yeah. So like the thing is, it's like there's a scenario we test positive, but that could be that we're sick, or it could be that we were healthy, right? So testing a mistake, but both of those would be a positive case or test positive. So we'll have to break this down, and we'll actually go through this in a second. But does this, at least this part make sense?
Good stuff. Yeah.
Okay, cool. All right, good question. I think this is helpful to clear this out before we dive into the math, because otherwise, if you're not clear on this part, the math's going to be even more confusing, right? So, okay, cool. So how do we build up this formula? So I'm going to build this up step by step. So we're going to use this guy. So just note that this is the same thing as saying probability of A such that probability of B. Good. Oh, Vero shared another video. I don't know what that is, but I'm sure it's relevant.
Well, that's the 3 blue, 1 brown.
Oh, good. Okay, good.
I watched it before I came on, and I'll tell you what, that visual representation really helps.
It does help, yeah. So we'll see if we can get into that. Yeah, he does a great job, by the way. 3 blue, 1 brown, visualizing a lot of mathematical stuff, and it just happened to do that. He just did probability. But anyway, maybe we'll go over that if we have some time. But yeah, so I'm just going mathematically first, and maybe we can break it out from there. So the equation right here, this is basically A such that B. So we can say I just put sick. So the event A is that I am sick with the disease, right? The event B is that I test positive. So you can say the probability of me being sick such that I tested positive is equal to the probability of that I test positive given that I'm sick times the probability of me being sick divided by the probability of being positive. So we actually know most of these things, if not all of it. We actually do know all of these parts, except for this guy right here. We just have to break it down a little bit. So we can kind of simplify this a little bit. So one thing to know is that it's like, okay, what's the chance, like this is what Akiva was just asking about a little bit, was that the probability of testing positive, right? Well, there's two possibilities, right? One is that we're sick, right, and we test positive. And there's a probability if we're healthy and we test positive, right? So we can actually break that down. So I wrote this down right here. Probability of testing positive, right, it's equal to, first of all, the probability of us being sick times the probability of us being positive, given that we're sick, right? Does that make sense? Okay. And then we also have to consider, like, what if we're not sick? What's the probability of us not being sick times the probability of testing positive that we're not sick? Does that make sense? Okay. So you can kind of think this real quickly, like we'll actually do these numbers in actually some code, but just kind of give it some numbers up front. It's like, okay, like what's the probability of us being sick? We know this, right? Like knowing nothing else, what's the probability of us being sick? It's just this guy right here.
0.01%.
Yeah. So we can say, I'll just put 0.0001, right? And that's times the probability of testing positive, given that we're sick. Do we know this number? I see a nod.
99%.
Yeah, 99%. And Jessica, where did we get this from?
The test is 99% accurate.
That's right.
Yeah, and tested positive.
Yeah, so because if we are sick, right, like 99% of the time the test will test us as positive, right? So this is 0.99. All right, so you can see kind of similar how we're gonna do this. And what's the probability of us not being sick?
.99%? Or wait,
Yeah,
the opposite of that.
yeah, 1 minus
There we go.
0.0, and I have the percents in there. It's this guy, 1 minus 0.0, right? Which is like, if I write this out, is 0.9999, all right? So I'll just put those guys down there, okay? And then that's times the probability of testing positive, but we're not sick. So what's this probability?
1%.
Yeah, 1%, right? So 1% of the time we make the mistake where we test positive even though we're not sick, right? And this is why I mentioned when I wrote this down is that it does matter about like whether you, how the test accuracy defines. Like maybe, for example, let's just pretend like the test is really good at identifying people who are sick, but if you're not sick, it like basically has to guess. Maybe the probabilities are different. But in this case, we're just gonna say they're the same. Does that make sense to people? Like why I make that distinction? Okay, cool. All right, so that's essentially what the probability is. And basically we can multiply all together and we can actually get a number of the probability of us being positive. Okay, so that's our first part. Like, cool, we can figure this out. Sweet. Can we figure out probability of sick? Yeah, we already figured that out, right? It was over right here. So we know this guy too. So the next part is gonna be probability of positive such that we're sick, right? Which is like, oh wait, we already know this too. We actually did this right here. Cool. So we actually know all these parts then. Pretty sweet, right? So basically we just fill these numbers out and we can figure out the actual answer that the chances of us being sick such that we tested positive. Okay, cool. Everyone follow me so far? All right, cool. All right, so let's just write our final equation. So if I wrote this all out here, I could write this whole big massive thing, right? And note that you can split this up even further if you wanted to, right? Like let's say there were more scenarios. Let's say like there's, this is in case we're sick versus not sick. Maybe there's like a third case scenario. I don't even know what that would be. But like there could be some other example of this, right? But the idea there is that this is encompassing all the probability of us testing positive. All right, so let's actually work it out, right? So we define the probabilities. So I'm actually gonna use some code here, right? So we're just gonna fill out like this guy right here. So we need, for example, the probability of us being sick. We said that's 0.001. P not sick, well, that's just 1 minus the probability of us being sick, right? Okay, so we got these values. Okay, and then we have the probability of being sick. Testing positive such, let's see, right, that's right. Yeah, the probability of being positive such that we're sick, right? So that means we are correctly identifying it. That's 0.99 or 0.99, 99%. Okay, and then the probability of us testing positive but we're not sick, that's 1 minus, in this case I wrote this here, this is actually technically, you know, I have to be a little more careful because this could be separate from here, but it's fine, right? So it's the same thing. Okay. Everyone following me so far? Just filling numbers. Okay, cool. And then I just basically multiply these together. Probability of being positive, we already broke this down here. I have all these parts defined, so I don't have to do anything extra. Just multiply those together. I was like, cool. So I have all the pieces, right? It's all set to go. So now I'm going to put the prior. The prior is basically, what's the probability of me being sick, right? So you can think of the prior being like, if I knew nothing else, I never took a test yet, I never had any symptoms or anything like that, the probability of having this disease is just simply just the probability within the population. So that's why we have P sick, okay? Our likelihood is our probability of being positive, right? Such that we're sick divided by the probability of being positive, right? So if you remember, just kind of reviewing this, this is our likelihood. So that's what we're looking at right here. So I have those two parts. So I have my prior, my likelihood, and then I made this little function because why not? We have our prior, likelihood, and to find our posterior, basically just multiply these together, right? Cool. So final result, right? So real quick, before we actually do this, right? The disease is 1 out of every 10,000 people have this rare disease. You test positive for this disease. How likely do you think you're sick? Any guesses? And these are all guesses. Like, you don't have to worry about trying to do the math right now. Like, we can figure this out, but like, what do you guys, what's your gut instinct kind of feel like? You test positive for a rare disease. The test is 99% accurate. Do you think you have disease? Do you think you don't have the disease? You have to put a number on it.
Probably have it.
Okay, probably. So give me a number between like, 0 and 100%.
99%.
99%. Okay, and then Jeffrey?
90, 91, 92.
91. So maybe not quite 99. So not like as certain as Kiva, but like a little bit lower than that. Anyone else want to take a guess? We'll find out in a second. That's all guesses. It's fine.
Do most people in the population fall on the side that's 1%? That 1% that test positive but are not positive. In other words,
are you just kind of thinking out loud, or?
Yeah, is there like a much like is the population that tests positive but is not sick is much larger than the population that tests positive and is sick, correct?
Right. Yeah, that's
1,000 times larger, right?
Mm-hmm.
So I think that increases the possibility that you're not sick.
Okay.
I don't know about how much, but I think it increases it. So
probably not still, like, you're thinking more on the lines of like, it's still lower, like, than at least what Jeffrey and Akiva are saying. Okay. Yeah. We'll say like maybe like 70%. Like that seems right. Shouldn't drastically do it that much. All right. All right. I won't call through everyone, but like, I want you to like think, like mentally think about that. Right. And so let's find out. We run the numbers in. 98% or 0.98%. So not 98%, but really, really low. Only 1% chance that you're actually sick. And you're like, whoa. Like, I don't know about you guys, but I'm like, wait, like I test positive for the disease that's 99% accurate. And I'm only 1% chance of actually being sick. And so this is actually what Avera was kind of saying too. You know, like you had the idea, but it's exactly these numbers. It's kind of tough to like say what that means. I think we might not have that intuition. But the concept was there, is that basically most people are not sick. Most people are perfectly healthy. The problem is that most people then will test positive for a test, right? Because that means, or I say most people, but most, a lot of people will test positive because they're healthy, and it just makes a 1% chance mistake.